Hi, my name is Rohan Kumar from Georgia Institute of Technology, and this is my Lab 6 presentation for Physics 2212. The primary goals of this lab was to observe the Faraday's law experimentally by measuring the time taken for a magnet to fall through an aluminum tube, simulate the scenario computationally using GlowScript, and finally analyze any discrepancies between experimental and computational data, similar to other labs done in the semester. Several important concepts underpin this lab. Faraday's law describes electromagnetic forces as a change in magnetic flux over time. Newton's second law relates net forces to momentum change. The magnetic force is represented by F equals current times the cross product of wire length and magnetic field. And Lenz's law indicates the direction of induced current opposing changes in magnetic flux. In our experiment, we used an aluminum tube of 0.3 meters long with an inner radius of 0.026 meters and a magnetic weight of 23 grams, which is estimated based on Amazon as we didn't have a specific weight measurement in the lab, with the magnetic dipole moment of 8.5 meters squared. Key assumptions were that the air resistance and external magnetic fields were negligible, and the tube was modeled as a multiple concentric rings. The computational model required defining variables like gravitational acceleration, magnetic dipole moment, magnetic dimensions, tube geometry, and resistivity. These parameters provided the basis for accurate simulating the magnet's behavior. The simulation also involved calculating magnetic flux through each ring in the aluminum tube. Flux was calculated by integrating the magnetic field over the cross-sectional area of each ring as the magnet passed through. Using GlowScript, the model incrementally computed induced currents and forces at small time steps. This approach allowed precise modeling of the magnet's acceleration and velocity as it moved through the tube. Both experimental and computational results showed slower times than freefall due to opposing magnetic fields generated by induced currents, consistent with Lenz's law. Our experimental time was 1.33 seconds, whereas our computational time was longer at 2.367 seconds, indicating a discrepancy of approximately 1.037 seconds. Some of the major sources of error could arise from assumption of neglecting air resistance, inaccuracy in magnetic dipole measurements, and possibly inaccurate timing techniques during the experiment, as there was a large amount of human error associated with starting and stopping the time, and even looking when doing video analysis and frame analysis as well. When analyzing the tube coloring, red indicating counterclockwise current and blue indicating clockwise current as depicted by Lenz's law, flipping the magnetic yield consistent results demonstrating induced currents always oppose the magnetic motion. For future improvements, incorporating air resistance, refining dipole moment accuracy, and ultimately reducing time step size would enhance precision of this lab. Analyzing the velocity versus time graph curve, gravitational force initially dominated, followed by reaching terminal velocity when magnetic and gravitational forces balanced. Hypothetically, decreasing resistance would strengthen the induced current and slow the magnet further. Conversely, introducing holes in the tube would reduce current and weaken opposing magnetic fields, allowing the magnet to fall faster, closer to what we traditionally see in free fall. This is a really interesting lab, and I enjoyed being able to work on this and be able to see this phenomenon in real life and not just in a lecture. Thank you.